I'm really glad to be here. And so indeed, I'm an applied analyst, and I became interested in some problems that arise from machine learning maybe 5-6 years ago. And it seems that some of the techniques that applied analysts know can be applied to data to show new results. And so I just wanted to show you somehow some of these techniques and how they apply to some of the machine learning problems. So my main collaborator, co-conspirator in this is Nicolas Garcia-Trios, who is now actually in Wisconsin, my former students. And then there is a number of people where we collaborated on problems related to clustering, on graph Laplacian, and problems in semi-supervised learning. There are, of course, many somehow related works, but probably today will not have much time to mention. So, okay, let me somehow introduce just one problem from machine learning as a motivation to study these techniques. So, okay, imagine that we want to do a clustering on a data set, right? So we would like to divide the data set into groups such that the elements in the group are more alike in some sense than elements between the groups. Even these MNIST images are relatively high dimensional, and in high dimension, right, so to do statistics, we somehow want to capture the low dimensional intrinsic structure of the data. And one way to access that is to assign a graph to this data set by connecting the vertices which are close enough in some sense, right? So either a KNN graph or a proximity graph with respect to some metric, right? And then the clustering problem becomes a graph partitioning problem. So we need to divide this graph into pieces in some way. Okay, so to make things mathematically precise today, so I will be studying data points which lie in R to the D, where, okay, initially D may be high dimensional. And okay, what we do, we connect the nearby vertices and obtain a weighted graph with the weights Wij. Then the right, so in the graph cut, what we will be measuring is the size of the graph cut. So namely, the sum of the weights of all the edges that go from one cluster A to the complement AC, right? That is the graph cut. So one can think, okay, maybe minimizing the graph cut would be a good idea for clustering, but okay, as this graph here shows, that is not universally so, because the minimal cut here would be just eliminating this outlier, right, and would not produce somehow desirable clustering. So what one would like, and what people have noticed maybe 15 years ago, is that one would like to introduce some balanced terms. There are many choices for balanced terms. What I will be saying applies to basically all of them. But I will talk, let's say, about the Cheeger cut. So in the Cheeger cut, you're minimizing the graph cut between the groups and divide it by the size of the smaller of the clusters. So size, in this case, for the Cheeger cut is measured by the number of vertices in the smaller cluster. So now cutting this one out is no longer viable, right? Because then the denominator would be very small, and that would not be a minimizer, but the minimal Cheeger cut is, in this case, something like this. So, okay, so how do we build the graphs, right? So there are two choices. So either we look at the proximity graphs. So if you take this kernel eta to be just a step function, right, which, okay, at some distance L, so we choose a distance L and say, if I'm within distance L, then I think that the images in this case are close enough, and I will connect them by an edge. Right, then you obtain what is called a random geometric graph, or we obtain a geometric graph, or you can take somehow more soft kernel, right, which smoothly decreases, but still somehow has some characteristic length scale above transitioning between somehow very strong connections and very weak connections. Another option is to look at KNN graphs, and in practice, actually, KNN graphs often work better. They somehow look more regular. The theoretical result that I will be talking about today apply to both proximity graphs and the KNN graphs, but somehow for actually simplicity, I will be only stating things for proximity-based graphs. Okay, so the task again, okay, if you have some data set, is to find a minimal Cheeger cut. I should mention that this is an NP-hard problem, right? On the other hand, if one looks at the data set that came as samples of some regular structures like what you see over here, right, then it seems that the methods, right, that actually have been first tried in imaging for segmentation problems do produce answers in a very reasonable times for graphs that have up to hundreds of thousands of vertices. So in particular, This group has used the primal dual method of Chambaud and Poc. Also, ADMM has been applied and again produces pretty good result. You cannot give a guarantee that this is a minimizer, but it is very likely that this is a very low energy configuration, so close in energy to the minimizer, right? Okay, so for the purposes later in the talk, because I would like to speak about functions on graphs and more general objective functionals, I will, instead of cuts, I will pose them somehow in a functional form over here. So, yeah.
Related to the previous one, are there any approximation guarantees for the objective?
No, right. I don't think that, right, no.
Not even in like some, if I guarantee that the point, this is that what you're going to show us? Like if
no.
the points are in 2D, for example, I can get some guarantees.
Yeah, I will not be showing guarantees. I think Sanjeev is visiting here soon, right? So he is a guy who would be able to somehow speak about the guarantees. But in terms of what I would like, so the guarantees that one can give is more of the type that, okay, I can find somehow a cut which is up to some constant, which is not very close to 1, or from the optimal cut. But that means in terms of whether that will give a good clustering, right, that is not somehow in that range, right? Because the energy of that would be somehow up to constant of the energy of the minimizer, right? Which doesn't tell you that the partitioning is similar, right? So in practical, somehow, in practical terms, I do not have any guarantees that the algorithms themselves produce something that is very close to the minimizer. But I will be working mostly under, let's look at the minimizers of discrete problems and see what they actually do. Right, so, given a function, right, which is now defined on the graph, so for every vertex I assign a real number, we define the graph total variation of this function as the weighted sum of the differences between the nodes connected by an edge. I note that, right, this generalizes the graph cut because the graph total variation of a characteristic function of a set, right, namely a function that takes values 1 and 0, depending whether the node belongs to the set or not, is the same as the graph cut. One other change that I did here, and this is hinting as to where I'm going, is I rescale this in a way that will make sense in the limit as n goes to infinity. Okay, so that is somehow not essential. It just makes stating my limits easier, right? But up to that constant, the graph total variation of a characteristic function is the same as the graph cut. We can also generalize the balance term. So the balance term is just the L1 difference to the median, right? So basically, it is the minimum over R, over all constants of the difference of the values at the nodes to that constant. We again notice that this balance function applied to the characteristic function of a set is again the same balance term that we had up to a constant. And okay, the relaxed problem that I will actually be studying is this functionalized Cheeger graph cut problem, namely dividing the graph total variation by this balance term over here. This relaxation in the kind of lingo of calculus variations is exact. Namely, if I have any function u that minimizes this problem over here, then almost every level set of u within the range of u is going to be a minimizer of the graph cut problem. And furthermore, if I have a minimizer of a graph cut problem, then I look at the characteristic function of that minimizer, so minimizer of this problem here. If I have a set A of nodes that minimizes it, I look at the characteristic function of that set, and that will be a minimizer of this problem here. So basically, these problems are, for practical purposes, equivalent. Okay, so what is that I will be studying? I will be studying is, okay, so the graphs that I will be studying here, I should think of as, or I will be thinking of as samples of some underlying measure, that I don't know somehow a priori. So basically, I have this ground truth assumption that what you see, right, namely those handwritten images, are samples of some measure of basically that would describe all the possible ways together with their frequency of how people write down digits, right? And what we are interested in are problems of consistency. So namely, is what I conclude for for some sample, right? Is that going to be true? Is that going to be stable if I have more and more sample points? And is that going to have some reasonable limit? And what does that limit represent? Okay, so I'm basically wondering, right? So somehow, if I draw a sample of a measure and I look at the clustering there, will that resemble some clustering of the, or some partitioning of the continuum underlying measure? So, okay. So this is the problem, right? Is as n goes to infinity, what do these discrete minimizers converge to? In what sense? And what does the limiting somehow object represent? So, okay. Well, yeah.
You always assume
Right.
2 clusters.
No, in our paper we did an arbitrary number of clusters, but we did not study somehow how should you choose that number of clusters, right?
So you choose it a priori
right.
first, and then.
Yes, right. One could look at actually the energy of clustering as something to base a decision on, right? You can see how the energy of the minimum clustering depends on the number of clusters and see if that jumps, but that is not something that we addressed in any way.
You care about A or GCA? I mean, you want to get the minimizer themselves,
Right.
some topology, or
Right. So actually, I care about both. So we'll prove the convergence of both. But personally, I care more about that the minimizers themselves converge to the minimizer in the limit, right? And I would say, okay, so if I go a little bit somehow in discussion, I would say, okay, once we identify this continuum problem, really that is somehow describing somehow what you would do if you had the full underlying measure available to you. So you still have a partitioning problem then. And I would like to turn things around, right? I would like to say modeling shouldn't be done on a continuum level. So this is where we decide what is my answer going to be if all the information was available to me. And then on a discrete level, what we should do is try to find an algorithms, a little bit like a numerical analyst would do. What is my algorithm to best approximate this continuum problem with discrete? Right now, this is, our approach was here not like that. Namely, we looked at the present approaches in the literature and looked at their limits. But in terms of kind of science and modeling, I think one should start here and then see how better to approximate it. And I would actually go on a limb and say that these are actually not very good approximations of this thing here. So with this, yeah, anyways. I would say one other thing that needs to be done here. So right now I just said, okay, I would like n to go to infinity. But when building the graph, right, we had that characteristic length scale, right, of the kernel, right? And as more data become available, I say that the length scale in that kernel should be taken to be smaller and smaller, right? So because that length scale of the kernel, right, so the L present in my eta, right, was not a matter of somehow desire, it was a matter of necessity. So namely, to build a geometric representation of my data, right, I needed to connect with something to obtain some of this geometric representation. If more and more data become available, right, so basically you're averaging the geometric information over the length scale L, and you're losing any information that is on a finer length scale than L. But as more data become available to you, right, you should really decrease your bandwidth, and you should resolve things at a finer bandwidth. So what we're saying is that as n goes to infinity, you should change your bandwidth from L to epsilon, right, and take the bandwidth to 0 as n goes to infinity. So, okay, in this case, I do it by looking at the kernel, which is a rescaled version of the original kernel. Again, this factor here is not so important, but so for the convergence of the minimizers, it is irrelevant. For the convergence of the value, that is where I need somehow these precise factors here in front. Okay, so basically now as n goes to infinity, I will change how my graph is built. I'm using this kernel to build a graph. So this is now this graph total variation in right, for the graph with n nodes and with bandwidth epsilon of n. The balance term doesn't change. And the question is, do minimizers of this functional converge to a minimizer of a continuum functional as n goes to infinity? Okay, so there are two questions, right? So how quickly should epsilon go to 0, and in what topology do I want to consider this minimization?
So
right.
for scaling, you kind of keep the degree constant.
Well, that will. Well, let's see. That actually will not really work, right? Because if you look at the random geometric graph with a constant degree, it becomes disconnected with in the limit with probability 1. So you need at least log n degree to be. If you look at the KNN graphs, you need the degree to grow at least as log n for the graph to remain connected. Yeah.
But you will have a giant.
Yeah, so that's a good question, right? So somehow, well, just restricting on a giant component, right, would not be enough because, again, you would have these outliers in some sense, but I agree that there exists a large structure so that if you restrict on that large structure, right, you would do well. Or I would actually say the following, right? So somehow there are probably better balanced terms than this one. Let's say if you look at biclustering, right? So clustering, balanced clustering in the rigid sense that you want both clusters to be of the same size, then probably you would not need that logarithmic factor over there, right? So to guess what the limit is, let's just look at these functionals. Okay, so the graph total variation, right? So it is this sum of, it is this graph cut in this graph with, it's the graph total variation here. If I introduce the empirical measure, right, to be, the sum of delta masses at the nodes, right, then this graph total variation can be written as this integral. But then as n goes to infinity, if I just look at the fixed function u, if I look at the fixed function u and I let n to go to infinity, well, then this is just a Monte Carlo integral, right, with respect to the product measure here of the integral of this function over here. And this function over here is nothing but a non-local total variation, right? And we know that the non-local total variation converges to the actual total variation as epsilon goes to 0. So if I take you see, this is not really what I should be doing, but for heuristics, I take the limit as n goes to 0 with epsilon fixed, and then I take the limit as epsilon goes to 0, and I do it for a fixed function u. I see that this graph total variation converges to this continuum total variation. So that gives me an idea as to what should I look at somehow in the limit, right? So in the limit, right, so we have, well, if I look at the parameter, right, then I notice that right here there is this weight rho squared, right? And rho is the density of the measure from which we are sampling, right? So rho is the density of this ground truth measure. So what I will have is that, right, okay, so this is this appropriate weighted total variation. I note that somehow, in terms of parameter, it corresponds to this weighted parameter. I just want to say that if you look at a set over here, you're really looking at, so the whole domain is called D. And if I look at the parameter of the set A, I only take the length of this black part over here. So that's why it's the relative parameter of A within D. Because that's really where the cut is, and that is what should be somehow considered in this functional. And that is what this total variation encodes. Now, of course, to do analysis, one needs to see, I would like to consider functions u, which are just a characteristic function of a set. In that case, right, the gradient doesn't exist. So we use the standard, weak definition of the total variation, which is written here. I'm not going to discuss it today, but okay, that's somehow the standard in the theory of BV spaces. So, given that total variation, right, we also we need to find what do we do with the balanced term. So balanced term would be just the lesser of the size of the clusters, but now the size of the clusters is measured as the measure of that underlying ground truth measure of your chosen cluster. And then the weighted Cheeger cut is minimize this weighted relative parameter of A divided by the balanced term described here. Or in the, yeah.
Sorry.
Yeah.
The limiting object u is a function on the space.
Yeah.
You want its minimizer to be the indicator of one side, say?
Yeah, well, that's what it will be.
Okay.
Right, so what I say here, right, is, okay, if I look at in a functionalized version, so then I have functions u, which are functions on the domain D, right? And I'm minimizing the weighted total variation divided by the balance term among this u. This relaxation of the cut problem is also exact. So namely, if I look at this function u, and I take arbitrary level set, right, then you obtain a set and its complement, and that set is going to be the minimizer of the continuum clustering problem. Right.
So I forgot the original setup of Cheeger original paper. How different is this from Cheeger original paper?
So,
on the manifold?
right. So the Cheeger. Yeah, so Cheeger, right. So yeah, so Cheeger, right, so that's a good question. So what is a Cheeger set compared to Cheeger cut? In the Cheeger set, you minimize the parameter divided by the area of that set itself, right? And here you're taking the minimum of the area of that set and of the complement. So this was introduced. I forgot who first introduced Chigger cuts and called it. It wasn't, so Chigger introduced Chigger sets, and then people in machine learning introduced Chigger cuts. Okay.
But I think the question also is, so how is this functional related to the perimeter? Like I mean, if you take, say, nu to be uniform on the manifold, is it?
Right, yeah. So this is, so again, you have that if you take a characteristic function of a set, then the total variation of the characteristic function is this parameter. Again, both of them are weighted by rho squared, and the parameter is relative to D. Right, okay, so the minimizer here, right, would be this, okay, symmetric object, right? And what we are wondering, right, are those discrete minimizers going to converge to this one? So, okay, now at least we have a, we don't yet have a conjecture, but I know which functions are involved, right? So I'm wondering whether the graph cut minimizers are going to converge to this minimizer here. I'm still not sure as to what scaling of epsilon and in what topology I should consider things. We note, right, so somehow for scaling of epsilon, right, you cannot take epsilon too small. If epsilon is too small, your graph doesn't capture the geometry of the underlying data set, and you can choose a minimal Chigger cut. Let's say I chose a particularly bad one here, because the energy of this cut between black and white is 0, so it is a minimizer. There are other minimizers, and it's far away from what you have there. If epsilon is too big, then you lose in resolution, which, okay, you cannot see here, right, because my perfect partitioning in continuum sense is actually plane, so you cannot see that it's getting worse if my resolution is decreasing, right? So there are a number of kind of results, consistency results in machine learning, right? But somehow, and actually, Arias, Castro, Pelletier, and Pudlo worked on this precise problem. But there are two things that our problem has, which are somehow the tools of statistics are not so well adapted to study. So namely, it is non-convex and non-linear, right? And basically just this is really something that has been studied somehow a lot in applied analysis. In particular, in calculus of variations, right, what we have here, we have a sequence of variational problems. Okay, they are discrete, right, and they depend on epsilon, and then I have a limiting problem in as epsilon goes to 0. This is precisely what people study a lot in calculus of variations. Let's say, they have elasticity theory for thin plates where the plate thickness goes to 0, right? Or even more closely to this, if you want to find a minimum of your variational problem, right, in PD or material science, right? So you discretize the problem. Then on a discrete level, you find a discrete minimizer. And now you're wondering, is my discrete minimizer close to the continuum minimizer that I want to find? And the tool that is used to study that is called the gamma convergence. So this was introduced in 70s by famous mathematician De Giorgi. And okay, I'll just somehow briefly recall it here. So we have a sequence of functionals, in this case parameterized by n, and you shouldn't think that this means discrete. It's just a sequence of functionals in some metric space, and I'm wondering, does this sequence of functional gamma converge to a limiting function which is defined on the same metric space? So if the gamma converges if two things are true. A lim-inf inequality, meaning that in some sense some lower semi-continuous envelope of the fn's is going to be bigger than f. So note that this is not the same as just lower semi-continuity of one function, right? Because here both the index of the functional and the index of a point considered are moving at the same time. And I also, well, this would just mean that f sits somehow below these guys, but they have to be connected more strongly. So the second, the lim sup inequality, or the recovery sequence, the existence of recovery sequence says that, well, for any element of the space, there exists a sequence of approximating y such that if I evaluate the approximating functional at the approximating y, I will be, if you combine these two things, it tells you that the limit is equal to f of y. So any value f of y is reachable as a limit of values of approximating functionals. Okay, the gamma convergence alone is not so useful, but if you can also show the compactness property, so namely that the boundedness of fn and boundedness of a sequence, then these two, just the boundedness in these two senses implies that the sequence has a convergent subsequence. If you can show both of these two things, then you can show that the minimizers of the approximating problem are converging to the minimizer of the limiting problem. So gamma convergence and compactness gives you what I'm after here, namely that approximate minimizers. And it's even true, it doesn't even have to be a minimizer, it can be an approximate minimizer. So if you had some guarantee for your numerical algorithm, that would be enough to reassure that we are converging to the right thing. So, yeah. Mm-hmm.
How does it relate to uniform convergence? I mean, if you just assume that Fn converges uniformly over some complex set.
Yeah, uniform convergence would be sufficient for gamma convergence, right? Pointwise convergence is not sufficient for gamma convergence, right? But the problem is that we don't have uniform convergence here. Actually, even the functionals are actually going to be acting on different kinds of objects, even though I'm going to put them in the same space here. So that's the typical situation, that you're very far from actually having uniform convergence. Okay, so right now, I recast the problem that I wanted is as the gamma convergence problem, and I'll say, note that the top part, right, has the derivative. The bottom part is a bulk term. In the bottom part, you actually have uniform convergence. So this guy does converge to this uniformly with respect to, the topology that I will be considering, which is pretty weak. But the top part does not, right? So the top part is a difficult part. So let me actually focus just on the top part for now and prove first the gamma convergence of the graph total variation to the continuum total variation. I still have these two questions as to how do I, connect these to, the discrete objects and the continuum objects. For the gamma convergence, I need to be able to put them all in the same space. And, right, so I have this problem, right, that I have some functions which are defined with respect to the continuum, right, that would be the limiting one, and I have a function which is defined with respect to discrete. I note that both of them are L1 functions. And I will also say one other thing somehow regarding gamma convergence. These two conditions are in tension. The stronger topology you choose, the easier it is to satisfy this. But if you have a strong topology, then boundedness of the functionals will not imply compactness. Okay, so this is resembling, I will have some graph version of TV. We know that TV, boundedness in BV spaces are compactly embedded in L1, right? So I could hope for compactness in L1. And that is really dictating that L1 topology is a good topology to consider in this problem. So basically, I consider the discrete objects as L1 functions with respect to empirical measure, the continuum objects as L1 functions with respect to the continuum measure. And I would like to compare them in a way that is consistent with L1 topology. And this was, so I should say, once we figured this part out, then the rest of it was kind of easy. So we basically have this toolbox of applied analysis. What was, for Nicholas and myself is really to figure out some of the, how do we put this problem that is posed on random discrete samples in this toolbox of analysis, right? So, so let's look at the situation here. So I have this discrete sample. I offset them a little bit so that we can see, it's complicated even like this. So anyways, I have a discrete measure, and I have a function on that measure where the values are represented by colors. And I have the continuum measure, and I have a function, which, I didn't use colors here, but you can see sort of what the values of u are. Now I would like to compare this un and u in some way which is consistent with L1 convergence. So bear with me with this graph. This is a little bit complicated, but let's try. So, so first look at a transport map. It doesn't have to be optimal. So basically you're looking at the coupling of these two measures, so the continuum measure and the discrete measure, So if I have a transport map, namely I push forward the continuum measure nu to the discrete measure nu n, then I can pull back my function un by that transport map. In that way, now I obtain these, you see this piecewise constant function over here, which is defined, which is an LP function with respect to the continuum measure. And now I can compare this piecewise constant function with my original function over here. Note that I would like to penalize both things. I would like to penalize both the LP difference between this composition, right, and how far did I use, transport in order to do that. So basically, I will only allow myself to compare close by points, right? Because if I allow to compare far away points, then, then you would end up that this function here, I don't know, u, and this function v would be basically at a distance 0, right? Because I can couple the opposite points in the measure where the values of u and v are the same. So basically, I'm I'm saying that for these two functions to be similar, I need to have points which are close by that have values which are close by, right? So, okay, and then, right, okay, so which transport map you take? Well, you take the best one in the sense that minimizes the sum of these two terms. So you take the infimum over all possible transport maps of this. Okay, this is still an auxiliary object. The real object is here. So we would like to consider general measures. So both measures can be discrete. So there may not be a transport map, but there is a transport plan. So we look at the infimum over all possible transport plans of the, the transport part and the value part. And we define now the space in which all of these functionals are going to be defined. So namely, my space is the space of pairs, a measure, and a function. So first I tell you what measure it is. It's discrete for a graph. It's continuum for the continuum measure, right? And this allows me to compare them. This is a metric space. It has a number of interesting properties. Namely, it is consistent with L1 topology. It does extend L1 topology. If I consider a sequence of functions with respect to the same measure, the convergence in TLP, it should be LP here. TLP is equivalent to LP, not L1, right? And also, you notice that, well, both of these terms are like transport terms. I mean, indeed, this is nothing else but, in some sense, it is equivalent to a transport distance between graphs of the functions. Now, okay, you could be a little bit confused here because the transport distances, they metrize the weak topology of measures. How do I say now that the weak convergence implies strong convergence? Well, it's the weak convergence of graphs. It is actually true that if you have that graph measures supported on the graphs of the function converge to an LP function, then the convergence in LP holds. Because again, right, if I have this function, I don't know, u, and I have these approximating function, highly oscillatory functions un, it is true that un converges weakly to u in L1, say, or L2, but it is not true that the measure supported on the graph of un converges in Wasserstein metric to the measure supported on the graph of u. These points are quite far away to those points. So again, the limit is as oscillations go to infinity, frequency goes to infinity, not as amplitude goes to infinity. This measure has a number of interesting properties that make it very convenient to work with. So somehow, actually, the choice of this transport map, as long as it is going to 0, doesn't matter for convergence. And this gives you somehow a lot of flexibility when working. It also allows you, let's say, you cannot look at compositions of LP functions, right? But you can consider compositions of TLP functions. And there are a number of other somehow useful properties. Okay, so now we have the topology. Let's look at the scaling. So here is the scaling, and here is our gamma convergence result. So let's look at somehow just dimension bigger than 3, right? So what we would like, right? So somehow, okay, since I didn't look at the, I'm looking at the random geometric graphs. So then if I'm in, one can do this on a manifold, right? But here we did it in assuming that we have a set of full measure, right? Omega, omega from which our points are sampled. So if omega is an open set, let's say in RD, right? And okay, I have n points in omega, then the typical distance between points in omega is like 1 over n to 1 over d, right? And what we are saying here is that we need log n to 1 over d more than that. So basically it is saying that the degree grows faster than log n. And for the Chigger cuts, so again, for this balanced term, this is optimal. Okay, so we also have the compactness, right, of course. And thus, this implies that the minimizers of this guy converge to minimizers of this guy, again, under these assumptions on epsilon. In dimension 2, there is an anomaly. Right, again, this is optimal in the sense that if your degree would be lower than log n, actually lower than some constant times log n, then the convergence of the minimizers in this problem would not hold. So we kind of, this I hope somehow validates that these tools from analysis are pretty good at addressing these problems because we were able to go all the way down to the practically optimal scaling for the epsilon for the convergence to hold. Right. Well, I will just say very briefly as to what is a key tool, right? So somehow I'm not going to show the proof, but one key tool in going between the discrete and the continuum world, so under the hood, are these estimates on the infinity transportation distance between the continuum measure and its empirical sample. So basically now you're looking at the coupling between these two measures, and you want to see what is the best coupling so that the maximal distance between the couple points is minimal. And the scaling for that is in dimension 3 and higher, right? It is has this scaling. In dimension 2 has the following scaling. So the expected scaling would be log n to 1 over d, and this is easy to explain. But in dimension 2, this dyadic, there is a dyadic method to do this, which was introduced by Aitoy, Komlosh, and Tushnadi, and at every level of this dyadic decomposition, you get the same contribution, and it's much harder to figure out what the limit is going to be. I'm mentioning this especially here because this was done at MIT. So this was in Peter Shor's thesis, right? So this was the first thing somehow he did, and it's really a phenomenal paper, right? So he did it for the square, and then we extended things. We extended things for general domains with general densities, and we actually used the proof, not the original proof, but a new proof by Talleyrand to extend that, right? So actually, in our technique, one can actually see that what we needed from the sequence of points, they don't have to be IID samples. The only thing that I need is that they are in some sort sense this epsilon net in this kind of transportation sense. So namely, if I can show that my sample points are within some distance measured by this infinity transport distance of nu, then the convergence holds. So if you have a grid, then you don't need a log n. You just need to go to infinity. We can also do this for graph Laplacians. So right in a graph Laplacian, okay, you look at the same weighted graph, but now your energy is going to be the graph Dirichlet energy. The graph Laplacian is obtained by first variation of this. You can look at the graph clustering, right? So namely, you construct the graph Laplacian, you find the eigenvectors, and then you embed your points into their coordinates by the first k eigenvectors, and then you, let's say, do k-means clustering on those. So basically, spectral clustering is not really a clustering method. It's just a nonlinear embedding, after which you use a standard clustering method. But it's similar to the Cheeger cut, right? But it's a relaxation of Cheeger cut, which is harder to compute, perhaps not quite as good, but okay. So again, the spectrum has a variation description via Courant-Fisher formula, right? And we can use this to show convergence again under the same conditions for epsilon, right? So you may think, so it's interesting, right? There were many, many results on graph Laplacians and so on. But if you carefully look at those results, let's say for spectral clustering, that the spectrum convergence and the eigenvectors convergence, either they are shown as for fixed epsilon, which was this von Laxburg, Belkin, Bosuke, right? Or they are shown as epsilon go to 0 at some unknown rate. So this would be like Belkin and Yogi. Or they are just pointwise result where the function u is fixed and you're not considering minimizers. So basically, okay, this was in our paper that Nicholas and I had in ACHA. I agree that these gamma convergence techniques are not what you should use for graph Laplacian. Graph Laplacian is both convex and linear. You can do better. And okay, so then that's the next thing somehow that we did. Okay, so first, okay, to convince you that we can actually do it on a manifold, let me do it on a manifold. So let M be a compact manifold. So now I'm working under manifold assumption. M is now the intrinsic dimension. Right. So what is the limiting object going to be? Limiting object is going to be described by this weighted Laplace-Beltrami operator. Again, this is a nice operator. It has a full spectrum. And if you have this nice convex linear problem, you can actually obtain error estimates, and that is what we did. This is in a preprint together with Matthias Hein and Moritz Gerlach, right? And we also quantify somehow how this error depends on what geometric properties of a manifold it depends. It depends on the sectional curvature and reactivity radius. So these are the elements of the intrinsic geometry, and R, the reach of the manifold, as an element of the extrinsic geometry. Yeah.
So here gamma is what?
Capital gamma.
Yes.
This is the graph, right? Okay.
So
Yeah.
is it nearest neighbor or what?
The same. No, the same graph. I'm not changing the graph construction. So I have the same random geometric graph with the same conditions on epsilon and n, right? And it's true also for k and n graphs. I mean, one could, this also follows for k and n graphs, right? So for the error, right? So, right, epsilon is, the bandwidth. So if I had a first order method to compute somehow the graph Laplacian, you would always have this error epsilon. So this is really a numerical error due to the bias. And this is an error due to the variance, right? So L is, I should have said what L is. So L is this length scale of optimal transportation. So this is this kind of length scale that describes the geometry, local geometry of the data set. So this is, so ln of n to 1 over d. So that is that length scale L that appears there. So basically, I need to choose, to obtain optimal error by our estimates, I need to choose epsilon to be much bigger than this local scale, right? Now, I believe that, if you're choosing IID points, this error rate is not optimal and could be improved, right? This would be part of a kind of a project in stochastic homogenization, which is a quickly developing field, but it is a very difficult thing. So if someone wants to discuss this, I would be happy to. So again, for IID points, this can probably be, or this can definitely be improved. But anyways, this is still the kind of a good step in towards proving those estimates. So okay, I'll skip this part. Huh?
So lambda is eigenvalue.
Oh yeah. Okay. So I should have. Right. We can do the same thing for eigen vectors and eigenfunctions. Only that.
TLP,
Yeah.
Is TLP for topology?
Sorry.
You compare and use this TLP like.
Yeah. Right. So you can use either TLP topology, but also you can. So there things are a little bit easier, right? Because eigenfunctions are very smooth, right? So you can actually, there you can just compare them by restricting to the sample, right? I mean, that's what people. I mean, I prefer TLP, but there you can use that as well, right? And we can again. So right, there is a full spectral convergence. There are kind of new phenomena if one looks at the TLP learning, but right. Let me mention actually something else that somehow is more recent, right? So somehow one other model that we are considering, right? So we were, our motivation was mathematical, but later we realized that it is probably a good idea to do this on a problems like this. So from Kaggle, one can download all of the prices of the houses sold in Seattle in 2015. So about 22,000 records, and here it shows a part of it. So all of these islands and so on are very well resolved, and you have a lot of houses on all of these. And okay, what we would like to do is, okay, so this is a price per square foot. So you would like to obtain a prediction for the price per square foot. So basically, in some way, you would like to denoise this. You would like to regularize, what you see over here, right? Because there are some variations for many, many reasons that are present. So I would like to smooth out, right, the labels that I see here, this price per square foot. But I would still like to allow for jumps, for discontinuities. Namely, right, it happens not too rarely, right, that there are two neighborhoods which are right next to each other that would have drastically different prices in real estate value. So basically, locally, right, so somehow there is a correlation between your houses and your neighbor's value, right? But you would also like to allow for transition boundaries which are may have jumps. So okay, so to do that, what we thought is maybe on a continuum level, right? I could think of the Mumford-Shah functional. So Mumford-Shah functional is this famous functional introduced in 1992 by Mumford and Shah in imaging, right? Which they said, somehow if you think of natural images, right? What you think of them is that they are more or less piecewise smooth plus texture, right? So right, you have, as the, objects can have sharp boundaries where there is a jump in the intensity, right? And some things can have texture, which is complicated, but more or less that is what it is, right? Piecewise smooth plus texture. Now, this does not allow for texture yet, but it does allow for piecewise smooth. So let's say if you have a signal f, and you would like to, or image f, and you would like to denoise it, right? Well, they say, okay, you would like to minimize this functional. What does it penalize? So first you have a fidelity term saying that you would like to be close to your function u. You have the smoothing term, right? So you have this Dirichlet term. So this is like in ridge regression, right? But you don't apply it everywhere. You only integrate over omega without the jump set of u, and then you penalize the size of the jump set. So this allows for discontinuity. It is not like ridge regression. It is even more kind of than the lasso, than the fused lasso, right? And okay, so what would be then the discrete version of that, right? So I was speaking about this with Antonin Chambaud, and he said, well, there is this paper by Gobino, right, where he introduced a non-local version of Mumford-Shah in order to approximate Mumford-Shah. And that non-local version of Mumford-Shah is actually something that directly modifies to graphs. And actually, right, I didn't mention somehow here, but at various stages you could see that the object on a graph is always closer to a non-local continuum functional than to the limiting function that you obtain somehow in the limit. That can be both for good and for bad, right? So somehow these non-local functionals do not have the full regularity of the local functionals, and that raises actually different technical difficulties, but they are also somehow what is somehow happening here. So okay, so this graph Mumford-Shah functional looks like this. So you have the fidelity term, but these two terms have been compressed into one term over here. And let me just show you how this function zeta looks like. So the function zeta is something like this. So it has a positive gradient at 0. It is concave, and it asymptotes to a finite value at infinity. So what this allows you is, depending on the values that you have here, right, whether they are small or large, you transition between two regions. If the values are small, right, then you're in a more or less linear region, and you recover this thing here, which recovers the Dirichlet energy. If these differences between the nodes are large, right, so then you're in this region, so zeta saturates, and you only obtain the size of the jump set. You no longer see the values of u. So this is, very clever of Gubino. And okay, so we can again show that the minimizers of this guy converge to minimizer of this guy, even actually in the presence of noise. So basically, if all of the labels that you measure have independent Gaussian noise, still the minimizers of this guy converge to the minimizer of this guy, which does not have noise, right? It's not that the minimizers converge to f, right? They converge to the minimizer, again, that you would say here. And okay, we also, so Chambaud, right, that was the algorithm of Chambaud and Pock, and he also worked on Mumford-Shah before, and this works really, really nicely, very quickly computes. Again, we cannot guarantee that this is a minimizer, but this is how those denoised labels look like. There are somehow many possible questions, but okay, I would be happy to discuss them if there are questions.
We have time for questions.
So in understanding the scaling of a kernel as n goes to infinity, especially towards the last part, if you use the sort of the transient of the random walk that corresponds to that Laplacian, the scale of that transient, would that have the same effect as this epsilon?
I don't know. I don't know. Right.
So basically what you're doing is right now you're just working with the eigenvector on the second part, which is like the steady state of that random walk.
Okay.
Now, you could, in principle, for clustering, use the transient as well. That could be corresponding to using a PageRank-like vector for clustering.
Right.
And that coefficient, that teleportation constant, would kind of work like a spatial scale. I was wondering if there's a connection between.
Yeah, I wouldn't know. I haven't thought of that. Right. It sounds like something that is plausible, but I have no.
So just a question of I mean, to me it sounded like most of the talk was actually low dimensional, right? So it's really
right.
we're constant and we're depending on D, and the picture. So I mean, how relevant is this technology for really problems that are really high dimension?
Well, Yeah, okay, right. So if the data is in full dimension, high dimension, then I say no, right? You know, somehow I think even this graph construction and so on, right, would be. I don't know that these would be good ideas, you know, kind of for clustering then, right? But if your intrinsic dimension is not so high, then the ambient dimension is actually not so relevant, right?
So you talked about this way of mapping your points to the original measure, right? It's TLP topology.
Right. Yeah.
Is there an easy way to understand why we need to do that? I mean, some easy way or some ad hoc way one could embed them in one would be take a kernel with a certain bandwidth.
Right. So like.
And smooth out your density somehow.
Right.
And still compute your original function on the discrete points and say that you have some continuity. But that probably fails, right?
Well, I don't know necessarily that it fails. I think for the Laplacian, right, for the estimates, right, that's actually connected with something that we do, right? If I don't have enough regularity, right, in my underlying function, I don't know how to carry this somehow in a very good way. Let's say in this way I obtain, let's say this mapping is an L1 isometry, right? So when I, the mapping, right, this composition, when I pull it back, it's an L1 isometry. If I did something with Voronoi cells or something like that, I really have no control on the L1 norm between one function and the modified function. And yeah, we were not able to work with that.
Okay. So in practice, if I want to somewhat extend UN outside the sample points,
right.
What would I do?
So yeah, right. Yeah, you cannot compute that. Let's say in the paper with the estimates, right? There we actually prove that since your objects are smooth enough, you can use the nearest neighbor extension and you're fine.
For the graph Laplacian or also for the TV?
For the graph Laplacian, right.
And for TV, is there an obvious way to do that?
Well, I would probably say that, okay, since you do have some regularity of these minimizers, that the nearest neighbor extension would again work, but we, haven't proved anything.
So I have one question. It's actually related to the question you had about the regularity and smoothing, for example. So when I look at those rates, it makes me think of non-parametric statistics, and here you have those asymptotic results, and say that if the bandwidth does not go to goes to zero fast enough, then you're actually good, right? Or it does not go to zero too fast is actually
right. Yeah.
And so to what extent is this?
Right.
Can this give me some? Yeah, so fast enough, I guess. Large enough. So the question I have is, to what extent can I adapt that to some underlying smoothness of the problem? So for example, if I promise to you that rho is going to be C22, can you actually
with the bound, right?
Faster as the bound? Is there? Is this technology sort of limited to the worst case, or is there a way to actually put in some smoothness in there, or will it adapt to smoothness, for example?
So I don't know. That would be more, I think, on the level of the rates, right? So somehow.
Yeah. But what I'm asking is, okay, let's say you can get rates.
Right.
The question is, do you need to modify the procedure to take advantage of faster rates, or do you think there's a sense according to which you think it might actually adapt to
right?
How
I would say one would need to adapt how the basically graph Laplacian is actually a very poor approximation of the Laplace-Beltrami operator. With that many available points, you should be able to build a better approximation of Laplace-Beltrami. With a better approximation, see, this only becomes consistent in the limit as n goes to 0. You see, when you are building the graph Laplacian, right? I give you these points. You're only taking, or one is only taking the distances and is throwing away all the information about the directions, right? There is a tremendous amount of information thrown away for no good reason, right? And so basically using a better approximation, just like people do in finite elements, right, would enable one to also, under smoothness assumption and so on, obtain, I don't know, second order rate of convergence and so on.
All right. Thank you very much. So I think since we're out of time, we're going to thank Dejan and take other questions.